In this video, we're going to have a look at resistors. Resistors come in different sizes. And when I mean sizes, I don't just mean the physical size. Resistors are used for all sorts of things. But underneath it all, the primary reason that we have resistance is to limit current. A small resistor, like this 1 ohm resistor here, will allow a fair bit of current to flow through it. A bigger resistor, like this 300 ohm resistor, will allow a lot less current to flow through it. Oh, look at that.
It's all stuck to the screwdriver. My screwdriver is magnetic.
Ohm's law says that if the voltage stays the same, as the resistance goes down, the current goes up. So this resistor here is a very small value resistor and a lot of current will flow through it. This means this resistor could get quite hot. And this is one of the reasons why resistors have different physical sizes. A big resistor like this one can handle more current and really more heat than a larger resistor like this one. This resistor can handle a lot less heat than this resistor. Resistors can be very tiny, like these surface mount resistors here. In fact, I've lost one. Where's that other little surface mount resistor gone? It's here somewhere. Oh, that's right, here it is. Some resistors can be really tiny, like these surface mount resistors here, or even tinier, like this little surface mount resistor here. It's interesting to think that this surface mount resistor and this resistor are nearly the same value, but this resistor is physically bigger and can dissipate a bit more heat. This resistor here is physically bigger again and can dissipate more heat as well. When you draw a resistor in a schematic, this is a symbol that can be used. This is the symbol for ohms. So this is a pretty old symbol and you won't see it used a lot anymore, but you may still see it around. You normally annotate the value of the resistor that you need in the circuit beside the symbol. It's more likely you'll see this as the annotation for a resistor. The symbol is just a little square and you write the value of the resistor inside the square. See how we don't use the ohms symbol. We just use the plain R. This is telling me that it's 100 ohms. How this R is used to annotate resistors in numbers is really quite widely used, and I thought we might have a quick look at it now. Let's have a look at these examples to annotate and write down resistance using this method. What you do is you substitute the R for the decimal point. So this is saying it's a 1.1 ohm resistor. This one is saying it's a 4.7 ohm resistor. This is saying it's a 22 ohm resistor. And this is fine for low values of resistance, but what if you want to write down a much higher value of resistance? Say you wanted to go to 1000 ohms. It's pretty easy to extend the idea. This is saying it's a 4.7 kilo ohm resistor, or a 47 kilo ohm resistor, or a 5.2 mega ohm resistor, or a 10 mega ohm resistor. This is nice and clear. It also means that you can't accidentally put the writing upside down. Let's have a little look at mounting a through-hole resistor. This is just a little example so that we can see how a resistor might fit inside a little bit of stripboard. See how the legs are nicely spaced out. There's no sharp turns in that resistor, and the turns in the legs of the resistor are far from the body of the resistor. Here I've got another resistor, and the legs of this resistor are bent way too close to the body of the resistor. If you bend the legs like this, it can break the join between the leg and the inside of the resistor, and what you're going to get is a resistor with infinite resistance, an open circuit in fact. What you need to do, if you're running out of space, is change the way the resistor sits and make it a bit more upright. Something like this. See how the legs of the resistor, they're not bent very close to the body. The sharp bend is up higher and it is really only a bend in the leg. You've got to consider also how the current might flow through the resistor. You want the current to flow through the resistor like this, up one leg, through the resistor, and out the other side. But wait, there's a trick. If you look underneath, you can see that there's a track that runs between the two legs. Between these 2 points, there's nearly no resistance, and current is going to follow the path of least resistance. So you think on the surface that you've got a resistor of a certain value, but in fact if you pay attention to that track underneath, you actually have no resistance at all. What you need to do is cut the track. See here I've got a little hole drilled in the copper track here, and what that's going to do is going to force the current to go up through the resistor and down the other side. In this way, you're going to force the resistor to be used. Here's a simulation of what we did before. You can see that the resistor is shorted out by that black jumper wire. And if I take it out, you can see the value of the resistor is now measured. Now there's one last type of resistor that I'd like to introduce you to, and this is a fuse. A fuse is a component that will break on purpose when there's too much current flowing through it. This fuse is rated for 0.5 amp. And you can see here that my multimeter is currently telling me that it's pushing nearly 1 amp through it. And as the current keeps continuing to go up, that fuse is glowing red hot, and very soon it's going to break. Sometimes people put fuses into their circuits to protect the rest of the circuit against something that may go wrong. It's kind of like a sacrificial defense. This fuse is called a slow blow fuse. That's because it takes quite some time for it to break. If you've got a big battery or a motor, you should put a fuse in the circuit. That's about it for resistors. Go resist something.